In 1978, amidst a global energy crisis, New Zealand envisioned something revolutionary: a city powered directly by the earth. Beneath the Taupō Volcanic Zone lay immense thermal heat waiting to be unlocked. Engineers and urban planners aimed to construct a fully integrated geothermal community. It was designed to harness subterranean steam for daily life, industries, and homes. But could a city truly run on the heat beneath its feet? The blueprints proposed an ambitious, zero-waste ecosystem utilizing direct geothermal energy. In 1973, the Arab oil embargo triggered a massive global energy crisis. Oil prices quadrupled almost overnight, causing widespread economic panic. Vulnerable island nations faced immediate fuel supply threats. New Zealand felt this sudden shock with extreme severity. Gas stations rationed fuel. Carless weekends were enforced strictly across the nation. Could a country survive without relying on foreign oil? National leaders searched urgently for long-term domestic energy solutions. Scientists turned toward New Zealand's unique geology for answers. The North Island sat directly upon active volcanic fault lines. Superheated subterranean water boiled continuously beneath the Earth's crust. Wairakei had already proven geothermal power was viable since 1958. Yet, electricity generation was only scratching the surface of this power. Planners envisioned utilizing raw geothermal fluid without conversion losses. Direct-use applications could power heavy industries and warm residential districts. Timber processing and industrial agriculture required constant, reliable thermal energy. Engineers began drafting radical infrastructure plans for volcanic zones. They mapped underground reservoirs to build self-sustaining industrial settlements. The oil crisis forced humanity to rethink urban energy systems completely. But could raw subterranean volcanic energy truly sustain an entire modern city? By 1978, field exploration reached an unprecedented momentum. Engineers focused their attention on the central Taupō Volcanic Zone. Broadlands and Ohaki geothermal fields became primary testing grounds. Heavy drilling rigs bored deep into dense subterranean rock strata. Pressurized steam roared violently from newly drilled test wells. Scientists measured reservoir temperatures, flow rates, and chemical compositions. Deep subterranean fluids carried immense energy, yet held hidden dangers. Could engineers tame this corrosive, high-pressure volcanic power safely? Geologists carefully analyzed complex underground fluid dynamics and chemistry. Minerals in geothermal fluids presented severe corrosion risks for metal pipes. Mineral scaling could clog distribution networks within mere months. Specialized metallurgy was required to withstand harsh subterranean chemistry. Researchers tested specialized alloys under extreme temperature and pressure conditions. Drilling teams mapped underground reservoirs with meticulous scientific precision. Data confirmed massive thermal capacity beneath the central North Island. Architects joined forces with geothermal engineers to draft blueprints. They conceptualized an integrated urban center built over active geothermal fields. Blueprints positioned heavy industrial zones closest to high-temperature steam wells. Timber drying plants and pulp mills required maximum thermal energy. Residential neighborhoods were strategically mapped further along distribution networks. Heat exchangers would safely transfer thermal energy into clean water networks. Insulated dual pipeline networks were designed to distribute continuous thermal energy. Urban planners prioritized efficiency, safety, and long-term sustainability. They carefully calculated pipe heat losses across vast urban distances. Advanced isolation valves were designed for localized system maintenance. Safety buffers separated residential housing from volatile high-pressure wellheads. Environmental impact assessments evaluated potential surface water contamination risks. Comprehensive technical blueprints proved a geothermal city was theoretically possible. 1979. The core principle was cascading thermal energy usage without waste. Superheated steam directly powered heavy industrial plants first. High-temperature timber drying and paper production received initial heat. Exhausted fluids still retained substantial thermal energy for secondary applications. Lower temperature fluid flowed directly into district heating networks. Radiators warmed thousands of homes and commercial buildings effortlessly. How far could a single drop of geothermal fluid truly go? This cascading system extracted every usable degree of thermal energy. Medium-temperature water circulated through extensive commercial greenhouse complexes. Year-round food production became possible despite harsh seasonal weather. Warm water then fed land-based aquaculture facilities for fish farming. Spent fluid was cooled safely before deep-ground reinjection. Reinjection preserved underground reservoir pressure and prevented surface subsidence. Every stage was interconnected into a perfect thermodynamic loop. The urban layout physically mirrored this precise thermal cascading sequence. Heavy industrial zones bordered high-temperature wellheads directly for efficiency. Mid-temperature residential districts formed the next concentric urban ring. Agricultural greenhouses and aquaculture ponds occupied outer suburban perimeters. Giant heat exchangers isolated toxic subterranean minerals from domestic water. Dual pipe systems supplied space heating and domestic hot water simultaneously. Waste heat ceased to exist in this carefully calculated urban ecosystem. Engineers solved complex fluid pressure and thermal dynamics challenges. Variable speed pumps adjusted fluid flow based on real-time weather demand. Advanced sensors monitored pipe corrosion and fluid mineralization constantly. Backup heat storage tanks guaranteed uninterrupted energy during well maintenance. The entire city functioned like a single, living thermodynamic organism. Human habitat matched the natural heat cycles of Earth perfectly. Would this closed-loop model actually survive real-world economic pressures? By 1981, harsh economic realities suddenly shattered the grand visionary blueprints. Building specialized geothermal distribution networks required massive upfront capital investments. Highly insulated pipelines and corrosion-resistant alloys proved astronomically expensive. Financing an entire specialized infrastructure strained national treasury reserves severely. High interest rates and global inflation crushed ambitious municipal budgets. Geological uncertainties added significant financial risks to the urban equation. Reservoir modeling was still developing during the early 1980s. Engineers worried about long-term pressure drops inside boiling geothermal fields. Clogging from mineral scaling posed constant, expensive maintenance headaches. Land subsidence risks raised serious concerns among cautious city planners. Unpredictable subterranean activity threatened the stability of permanent urban structures. Was building over volatile volcanic fields too dangerous a gamble? Political priorities shifted dramatically under New Zealand's changing national leadership. The government launched the aggressive Think Big economic industrial program. State capital moved toward massive synthetic fuel and natural gas projects. Large-scale industrial developments swallowed available national energy sector funding completely. Experimental geothermal settlements lost political momentum and government backing rapidly. The visionary urban plans were quietly shelved in official archives. What if that geothermal city had actually been built in 1978? Imagine walking through a thriving metropolis heated entirely by volcanic earth. Steam rises silently from sleek, integrated urban infrastructure across the skyline. Greenhouses produce fresh food year-round without fossil fuel consumption. Industries run cleanly on endless subterranean heat without carbon emissions. How would our modern cities look if this bold vision succeeded? Could have served as the ultimate global model for sustainability. Urban planners worldwide might have replicated this zero-carbon blueprint everywhere. New Zealand would have led a green energy revolution decades ago. Although the geothermal city was never built, its blueprints were not wasted. The rigorous research conducted throughout the 1970s laid crucial scientific foundations. Engineers gained invaluable insights into reservoir mechanics, fluid chemistry, and thermodynamics. Techniques developed for pipe corrosion control transformed modern industrial engineering forever. Today, New Zealand stands as a global leader in direct geothermal application. Commercial greenhouses and timber drying plants now utilize these pioneer principles daily. Rotorua and Taupō harness direct thermal heating for various municipal services. Modern eco-industrial parks worldwide apply these exact thermodynamic cascading principles. Industrial waste heat is redirected to maximize total system energy efficiency. Closed-loop engineering concepts from 1978 paved the path for decarbonization. Scientists learned how to re-inject fluids safely to sustain underground pressure. Environmental safeguards established during those trials now protect fragile geothermal ecosystems. Geothermal power stations currently supply significant clean electricity to national grids. Could an ambitious failure hold the secret key to our future energy transition? The vision of 1978 proved that humanity can coexist with volcanic forces. As the world races toward zero-emission urban development, these blueprints re-emerge. True innovation often lies not in completion, but in pioneering ideas. Earth still holds boundless heat directly beneath our restless feet. Will we finally build the geothermal cities of tomorrow?